Level 0. The sky is quiet. The sun stares down like a glowing eye, calm and unwavering. But that calm is an illusion. Even in its stillest moments, the sun is boiling. Plasma churns in convection cells the size of continents. Magnetic fields twist beneath its surface like coiled serpents. But none of that reaches Earth. Not yet. Level 0 is what space weather experts call background flux. This is when the sun is at rest, magnetically speaking. It's the baseline, the quiet hum of solar activity. At this level, any radiation emitted is weak, classified as A-class on the X-ray scale used by NOAA and NASA. You wouldn't even notice. Satellites operate flawlessly. GPS signals flow like uninterrupted streams. Astronauts in orbit might snap photos, unfazed by radiation levels. The sun, for now, is just light and heat. But make no mistake, beneath this serene mask, magnetic stress is building. The corona, that outer layer of solar atmosphere, simmers at over 1,000,000 degrees Celsius, held together by tension. Invisible ropes of magnetism are twisting tighter by the hour. Solar minimum is not peace, it's patience. Even in quiet years, more energy is circulating through the sun's magnetic field than humanity has ever generated, and when that field snaps, it won't stay quiet. This is the ground floor before ignition. When solar flares begin, level 0 becomes the launch pad. Level 1, the first spark, an active region on the sun, a cluster of dark sunspots, starts to twist. Magnetic lines cross and tangle, and then they break. This is a B-class flare, the smallest measurable type. Technically, a flare, but barely above noise. It releases energy equivalent to a few 100,000 nuclear bombs, but in cosmic terms, it's a whisper. You'd need sensitive X-ray instruments to even notice. On Earth, you feel nothing. At most, a weather satellite might log a blip, maybe a slight uptick in high-frequency radio interference. But even then, it's fleeting. The flare itself erupts in under 10 minutes. No coronal mass ejection, no auroras, just a tiny spark of X-rays, UV radiation, and fast electrons pouring into space. Scientists don't even issue alerts for B-class flares, but that doesn't mean they're pointless. They're signs. Sunspots are magnetic scars, and when a region starts producing B flares, it's often ramping up towards something bigger. Think of it like creaking timbers before a collapse. If a sunspot cluster starts throwing out multiple B-class flares in a day, that's a fuse burning in real time. Level 2. Now the sun clears its throat. C-class flares are no longer whispers. They're murmurs with muscle, strong enough to register on Earth, not strong enough to do damage, but enough to be noticed. These flares emerge from sunspot regions undergoing moderate magnetic stress. They're often accompanied by surges of extreme ultraviolet light, sudden ionospheric disturbances, and occasional Type 3 radio bursts, the sound of solar particles screaming through interplanetary space. Imagine standing on a beach as distant thunder rolls overhead. You don't see the storm, but you know it's out there. That's what a C-class flare is. For communication engineers and airline navigators, Level 2 is the line where solar flares start to matter. A strong enough C flare can temporarily degrade shortwave radio over the sunlit side of Earth, particularly over the Pacific and equatorial regions. Polar flight paths, used by airlines to cut hours off travel, sometimes get rerouted to avoid weak solar storms like these. And for space agencies, this is the early warning threshold, the point where satellites begin logging UV-induced heating in Earth's upper atmosphere, causing orbital decay, fuel adjustments, and mission recalibrations. Even a small C flare adds drag to satellites by swelling the thermosphere like a balloon. But again, the real story is magnetic. If a solar region consistently throws out C-class flares, it's usually sitting on tangled fields, teetering on instability. Think of C flares as a poker tell. The sun is bluffing, and soon it might go all in. Level 3. Then it happens. The real flash, M-class. This is where solar flares become dangerous. One eruption can release energy equivalent to 1 billion hydrogen bombs. On Earth, the effect is instant. X-rays and extreme UV light slam into the dayside ionosphere, triggering sudden D-layer absorption, a full-on radio blackout across high-frequency, HF bands used by ships, planes, and emergency services. Level 3 flares are known to knock out aviation comms, drown AM radio in static, and overload signal processors on satellites. If the flare lasts long enough, say 10 to 30 minutes, even GPS becomes unreliable. Positioning errors spike. Time synchronization systems drift. But the scariest part isn't the radiation. It's what comes after. Many M-class flares are linked to coronal mass ejections, massive plumes of magnetized plasma hurled toward Earth at speeds up to 3 million kilometers per hour. These CMEs take a day or two to arrive, but when they do, they can trigger geomagnetic storms, auroras, and even transformer-frying power surges. An M-class flare with a direct CME is like the muzzle flash before a cannonball, and history shows how deadly that can be. In 1989, an M-class flare and associated CME caused a blackout in Quebec, plunging 6 million people into darkness. Transformers exploded, satellites lost altitude, it took 9 hours to restore the grid. That wasn't a worst case, it was a preview. Level 4. Now we climb the scale into rare territory, the X-class flare. This is the top tier of solar classification, and where things get truly explosive. An X 1.0 flare is 10 times more powerful than an M 1.0, but the scale isn't capped, it keeps going. There have been flares at X2, X9, even X28. The energy released? Up to 10 to the 32nd power ergs, roughly the combined yield of every nuclear bomb ever detonated, times 1,000. These flares are blinding. In X-rays, they overwhelm instruments. The sun lights up like a flashbang. To a space observer like SOHO or SDO, the brightness saturates sensors. NASA sometimes issues saturation warnings because the detectors literally max out. To Earth, the impact is immediate and multi-layered. Radio blackout across half the globe, GPS jamming, airline comms failure, solar energetic particles (SEPs) hitting the magnetosphere like a barrage of bullets. Some SEPs move so fast they arrive within minutes, penetrating spacecraft electronics, endangering astronauts, even triggering secondary radiation inside aircraft flying near the poles. And then comes the CME. If Earth is in the line of fire, prepare for auroras and possibly outages. The most powerful solar storm in recorded history, the Carrington event of 1859, is believed to have been driven by an X40+ class flare. Telegraph systems sparked, caught fire, and worked even with batteries disconnected. Auroras danced over Cuba and Colombia. If a Carrington-level event happened today, it could cause $1 to $2 trillion in global damage, mostly to power grids, satellite constellations, and long-range comms. And remember, we've already seen an X-28 in modern times. It happened in 2003. That flare knocked out Japanese satellites and forced NASA to reroute astronauts inside shielded modules aboard the ISS. We got lucky. The flare was slightly off angle. The next one might not be. Level 5. Now we're beyond the known. The Super X class. This is a hypothetical level. A flare beyond X50, X100, maybe even X200. Magnitudes we've never directly observed, but science suggests are possible. How? By studying other stars. Astronomers have witnessed super flares from sun-like stars, eruptions thousands of times more powerful than anything our sun has thrown in modern history. In 2020, scientists documented a superflare from a G-type star just 100 light-years away. If a similar event erupted from our sun, it could destroy satellite networks, strip parts of the ozone layer, and cause radiation exposure on aircraft. Earth's magnetosphere would survive, but barely. GPS constellations? Gone. Long-haul flights? Grounded. Power grids? Severely damaged. Could our sun produce one? Unclear. But historical tree ring data from ice cores in Greenland and Antarctica reveal spikes in radioactive isotopes like carbon-14 and beryllium-10 that some scientists attribute to ancient superflares, possibly in 774 AD and 993 AD. Those events left no visible damage, but that was before we built a civilization on electronics. If a Super X-class flare erupted tomorrow, we might lose communication with half the planet in seconds and face months, if not years, of blackout recovery. This isn't science fiction, it's astrophysical potential. The sun, for all its light and warmth, holds the power to reset civilization with a flash. Level 6. The flare isn't bright, it's blinding, a burst so intense it overwhelms sensors on satellites. Instruments meant to measure X-rays saturate, pegged at their max. This is the start of an X-class solar flare. You're not just dealing with energy, you're witnessing the sun's magnetic field snapping and reconnecting in a split second, releasing more energy than 1 billion hydrogen bombs. This flare can last minutes, sometimes hours. But the damage? That can linger for days. At this level, radiation floods near-Earth space. High-frequency radio communications are blacked out over an entire hemisphere, especially affecting aviation routes near the poles. GPS signals begin to stutter. Solar observatories scramble to track its companion, a coronal mass ejection, or CME, that might be on its way. We've entered serious territory, not just science, but risk, because this is the threshold where space weather becomes a global concern, not just an astrophysical curiosity. In 2012, an X-class flare erupted from a sunspot cluster known as AR-1520. The resulting CME missed Earth by just 9 days. Had it struck, scientists estimate it could have triggered a geomagnetic storm matching the infamous Carrington event. Even modern spacecraft have trouble capturing the full scale of energy involved in X-class events. Many readings go off the charts. Level 7. A flare cracks through the corona, but this time it's eruptive, meaning it's not alone. Behind it, a full halo CME spreads like an expanding ripple through the solar system. It's Earth-directed. This is no longer just light or particles. It's mass. Billions of tons of solar plasma traveling at up to 3,000 kilometers per second. And when it slams into Earth's magnetic field, that's when the real show begins. The magnetosphere begins to groan. Satellites are bombarded. Power grids hum with strange fluctuations. Transformers heat up. In 1989, a CME triggered a massive blackout across Quebec, collapsing the electrical grid in under 2 minutes. But here's the real danger. CMEs don't arrive alone. They often carry shockwaves ahead of them, compressing Earth's magnetic field, injecting energetic particles into the Van Allen belts, and causing radiation levels to spike on commercial flights and in spacecraft. Auroras explode across latitudes as low as Texas and southern France. What starts as a flash on the sun ends with blackouts, broadcast disruptions, and beautiful, but ominous, light shows on Earth. Airlines today routinely reroute flights away from polar regions during major solar events to reduce crew and passenger radiation exposure. Level 8. Now the timeline tightens. A series of flares, not just one, begin erupting from the same active region. These are known as flare storms, rapid-fire X-class emissions from magnetically complex sunspots. The worst part? Each one weakens Earth's shielding just a little more, like punches softening up a boxer before the knockout blow. In late October 2003, a flare storm known as the Halloween storms produced multiple X-class flares, including an X-17.2 on October 28th. It was followed by one of the most powerful CMEs ever recorded. Satellites shut down. Astronauts aboard the ISS took shelter in shielded areas. Air traffic was rerouted globally, and solar radiation disabled the Japanese ADEOS-2 satellite entirely. What makes flare storms terrifying is the cumulative impact. Each flare heats the upper atmosphere, causing it to expand. This increases drag on satellites and space debris, leading to collisions, deorbiting, or unexpected failures. And sometimes, the biggest flare isn't the first, it's the one that comes when defenses are already compromised. During flare storms, GPS accuracy can degrade by over 50%, impacting everything from banking systems to precision agriculture. Level 9. This level isn't just rare, it's legendary. A single Earth-facing X-class flare breaks every previous record. Sensors max out. Satellites report a saturation event and fail to return proper data. The only estimate? Somewhere above 30, possibly 40, or even 50. We're talking about a release of energy equivalent to millions of 100 megaton nuclear bombs, all unleashed in under an hour. In November 2003, an X-28 plus flare exploded from the Sun. It was so intense that solar measurement instruments on the GOES satellites couldn't register its full strength. Later analysis suggested it might have been closer to X-45, the largest recorded in observational history. Luckily, the flare was only partially Earth-directed. Had it been a direct hit, the resulting radiation storm and geomagnetic disturbance might have brought down entire sections of the internet backbone, knocked out power grids across continents, and degraded GPS networks for weeks. This is the level where critical infrastructure risk becomes planetary, where global finance, transportation, and communication systems are all vulnerable simultaneously. In response, agencies like NASA and NOAA now maintain constant solar monitoring and have begun integrating space weather warnings into aviation and telecom protocols. Level 10. We now leave history and enter possibility. Level 10 represents a Carrington-class event in modern times. In 1859, telegraph systems across Europe and North America sparked, burst into flame, and kept working even after being disconnected from power, all because of a solar storm. Today, the consequences would be orders of magnitude worse. A flare this strong would not only cause radio blackouts and satellite disruptions, it would likely overload entire power grids, damage transformers that take years to replace, interrupt submarine cable repeaters, cause aviation to grind to a halt. It could result in a global internet blackout, depending on how interconnected backbone systems respond to geomagnetic currents. Banks, airports, hospitals, water treatment plants, all would be at risk. In 2013, Lloyd's of London estimated that a Carrington-style event today could result in up to $2.6 trillion in economic losses. And that's just the US. What makes this level especially cruel is its speed. A fast-moving CME can reach Earth in under 18 hours. That's your window. The 1859 Carrington flare ignited auroras so bright that people in Cuba could read by their light at midnight. Level 11. You'd think we've hit the limit, but now imagine this, a superflare, the kind detected on stars like our Sun, but 10 to 1,000 times more powerful. NASA's Kepler mission has identified superflares on Sun-like stars across the galaxy. These flares dwarf anything in human memory. A single event could strip the atmosphere from an Earth-like planet, sterilize its surface, or cause extinction-level consequences. Now, could our Sun do it? Some scientists say yes. Others say it's statistically unlikely, but not impossible. Ancient tree rings show spikes in carbon-14 in 774 and 993 AD that might correlate with extreme solar events. These aren't proven superflares, but they hint that the Sun can get much angrier than we've ever seen. A superflare on the Sun might deliver energy in the petajoule range, enough to ignite electronics across entire continents and cook the upper atmosphere, changing weather patterns for years. We might not just lose the grid, we might lose satellites, ozone, and the magnetosphere's protective layer, and we might never see it coming because superflare precursors remain poorly understood. Level 12. Now we cross from rare to speculative. Imagine a magnetic hyperflare caused by solar interaction with an interstellar anomaly, a rogue magnetic field, a passing stellar current sheet, or an exotic disturbance in the heliosphere. This event doesn't follow traditional solar cycles. It doesn't come from a sunspot. It comes from a complete reorganization of the Sun's magnetic skeleton, triggered externally or internally. The result? A global solar flare, releasing energy not from a localized region but from the Sun's entire surface. A planetary hemispheric flash, enough to damage the magnetosphere, disrupt biological circadian rhythms, and collapse every electrical and communication grid on Earth in seconds. This would not be a storm. It would be a solar hurricane. At this level, shielding satellites or turning off the grid wouldn't be enough. We'd need to redesign our technology to survive in a post-electric environment, at least temporarily. No such flare has been seen, yet. But models suggest it's possible on stars undergoing magnetic field reversals or stellar aging transitions. In 2020, NASA's Parker Solar Probe observed magnetic switchbacks and rotational jets that suggest our understanding of solar energy storage is still evolving and possibly incomplete. If the sun can change the world in minutes, don't miss what it does next. Subscribe for more.